All right, let's talk about the p-value. It's one of the most common and, let's be honest, one of the most confusing concepts in all of statistics. It's this tiny little number that ends up carrying a ton of weight in scientific research, so we're going to demystify it.
I'm sure you've seen this before, right? You're reading about some study and you see p less than 0.05. It's everywhere. But what does that little letter p and the number after it actually mean? What is it telling us? Well, that's exactly what we're going to break down.
And here's how we'll do it. We'll start with the kind of big question that p-values help us answer. Then we'll get right into what a p-value is. After that, we'll see how you even get one from data, touch on a key difference in how tests are run, and finally, wrap it all up with the final verdict.
Okay, first things first. P-values don't just exist on their own, floating in space. They are a really important part of a process called hypothesis testing. And that's basically just the formal way scientists and researchers test out their ideas.
So, at the very heart of any statistical test, you've got these two competing ideas. On one side, there's the null hypothesis. You can think of this as the status quo, the nothing interesting is going on here theory. It's the default assumption. And on the other side, you have the alternative hypothesis. This is the exciting one. This is the theory the researcher's actually curious about. The idea that, hey, maybe something is happening here.
And this is absolutely crucial to understand. We never set out to prove the null hypothesis. The whole point of the experiment, the whole game, is to see if we can collect enough evidence, enough compelling data to be able to reject that boring nothing is going on theory and instead favor our alternative. Okay, so now that we have that background, let's bring in the star of our show. What is a p-value? We're going to start with a really simple, intuitive way of thinking about it, and then we'll get to the more formal textbook version.
So here's the easiest way to wrap your head around it. A p-value is simply the probability that your data supports the null hypothesis. It's a measure of how well your results fit in with that nothing is going on world.
So let's see how that works. If you run your experiment and you get a large p-value, something like 0.836, that means your data looks pretty consistent with the null hypothesis. It's not surprising at all. But if you get a small p-value, say 0.022, that means there's a really low probability your data supports the null. It suggests your results would be pretty rare if nothing was going on, which makes you suspicious.
Now, that intuitive definition is a fantastic starting point. But for all the statisticians out there, you know the formal definition is a little bit more specific, a little more nuanced. So let's take a look at that.
Okay, here it is. The p-value is the probability of getting your results, or results even more extreme, if we assume the null hypothesis is true. So when you get a small p-value, what you're really saying is, wow, if nothing were actually going on, it would be super unlikely to see data like this. So maybe something is going on after all.
So how do we actually get this number? Where does it come from? Well, the specific math can get complicated and changes based on what you're testing. But the overall process, the journey from data to p-value, is actually pretty logical.
It basically works in 4 steps. 1. You state your two hypotheses, the null and the alternative. 2. You go out and collect your data. And then you crunch it all down into a single number called a test statistic. 3. You use that test statistic to calculate your p-value. And then 4. The final step, you compare that p-value to a cutoff point to make your decision.
And what's really cool is that this basic process is used all over the place in statistics. It doesn't matter if you're using a t-test, a z-test, a chi-square test, or even something called a NOVA. They're all designed for different situations, but they all end up giving you that all-important p-value.
So you've got your p-value. Now what? Well, how you interpret it depends on a choice the researcher has to make before they even start. Are they doing a one-tailed test or a two-tailed test? You see this number all the time, 0.05. This is the most common significance level, what scientists call alpha. It's basically the line in the sand. If our p-value falls below this number, we generally agree that our result is statistically significant, meaning it's probably not just due to random chance.
So how you use that 0.05 cutoff depends on your test. A two-tailed test is kind of the default. It's looking for any difference at all, either greater than or less than what you'd expect. So it has to split that significance level in half. A one-tailed test, though, is much more focused. It's only looking for an effect in one specific direction, so it gets to put all its statistical power, that whole 0.05, into just one end of the distribution.
Right, so you might be wondering, if a one-tailed test has more power to find an effect in a specific direction, why wouldn't you just use it all the time? When is it actually the right call to make?
Well, it really comes down to this. You can only use it when you have a very strong reason to believe an effect will only go in one direction, and you truly don't care if it happens to go in the other. Here's the classic example: a new, cheaper version of a drug. All you really need to prove is that it's not worse than the expensive one. You only care about that one direction. If it turns out to be better, that's just a bonus, but it's not what you needed to test for.
All right, let's pull all these threads together. We've talked about hypotheses, calculating p-values, and how we interpret them. So what's the big takeaway from all this?
If you remember just one thing, let it be this. When you get a small p-value, usually one that's less than 0.05, that is your signal. That is the statistical evidence you need to reject the null hypothesis. It's the green light to say, hey, it looks like something interesting really is happening here.
And here's another neat way to think about it that connects it to another concept you might have heard of: confidence intervals. A p-value of exactly 0.05 means that the 95% confidence interval for your result just barely touches zero. So if your p-value is less than 0.05, your confidence interval won't include zero at all, which is just another way of saying your result is statistically significant.
And we'll leave you with this one last really important thought. A p-value is great at telling you if a result is statistically significant, if it's unlikely to be a random fluke, but it tells you nothing about whether that result is practically important. You can get a tiny p-value for an effect that is so small it's completely meaningless in the real world. So the p-value is a powerful tool for sure, but it's only one part of the story.